Chemistry, we're on to our last lesson in Unit 6 on covalent and ionic compounds, and this deals with the concepts of formal charge and resonance. So we know that oxygen in its atomic state is a neutral atom with 6 valence electrons. And if you don't remember how to do that, come ask me, but it's how many elements from the left in its row. So oxygen is the 6th element from the left in the second row. That means it has 6 valence electrons. Formal charge is a way of determining the charge on an atom involved in a covalent bond. If the formal charge is different than the normal valence charge of the atom, 6 in the case of oxygen, then the atom and overall molecule is less stable. But if the charge, while it's inside a molecular structure, is the same as its normal valence charge, so 6 in the case of oxygen, then it's going to be stable. Nature prefers the most stable configuration of a molecule. The formal charge of an atom is given by the formula. Formal charge equals the number of valence electrons. Now that's when it's in its natural state without being bonded to anything. So again, in the case of oxygen, that's 6. Now the next two numbers deal with what is its configuration inside the molecule. So it's minus the number of lone pair electrons it has, and then minus 1/2 of the bonding electrons that it has. So example, both of the following configurations can be formed using the rules of covalent bonds. So there you have two carbon dioxide molecules. The one on the left is the one you recognize as being the normal way that we would draw a carbon dioxide molecule. The one on the right looks kind of funny. It's got a single bond on one side of the carbon and a triple bond on the other side. But how do we know that's not the correct configuration of a carbon dioxide? So we're going to go ahead and do a formal charge calculation here. So we take the oxygen on the left and we just follow the formula. The number of valence electrons that oxygen has in its natural state when it's not bonded is 6. Then we look at that and we see that that oxygen molecule has 4 lone pair electrons. Now it's not the number of lone pairs. There's 2 lone pairs on that oxygen, but it's 4 lone pair electrons. So you count all the electrons in this case. And then we see that there are 4 bonding electrons between the oxygen on the left and the carbon. It's a double bond. So you take half of those. Half of those 4 we're going to say belong to the oxygen, and the other half belong to the carbon. So the half that belongs to the oxygen, we're going to subtract that out. And so when we do that, we end up with a number of 0. So oxygen naturally has 6 valence electrons, and in this configuration, it also has 6 valence electrons. The reason we use this subtraction method in this equation is so that all atoms that are stable will end up having the formal charge formula going to 0. It won't be different for different atoms with different numbers of valence electrons. So 6 is the normal valence charge, number of valence electrons on an oxygen. 4 is the number of lone pairs in this particular molecular configuration, 4 lone pair electrons. And then half of the bonding electrons, there are 4 bonding electrons, and half of those belong to oxygen, so we subtract that out and we get to 0. So oxygen has 6 valence electrons, oxygen has 4 lone pair electrons, and we take half of the bonding electrons and we follow the formula, we get to 0. Now we're going to take carbon. Carbon, if you look at on your periodic table, is the 4th element from the left on the second row. So it has 4 valence electrons. Now in this particular molecule, the next two numbers deal with this particular molecule. It has no lone pair electrons, the carbon in the center. And then if you look at inside that red box, it has 8 bonding electrons, 4 on the left and 4 on the right. So you take half of that number. So half of 8 is 4. So it becomes 4 minus 0 minus 4 equals 0. So that's also a very stable configuration, the most stable configuration for that carbon. Carbon has 4 valence electrons. Carbon has no lone pair electrons. And we take half of the bonding electrons. Now we're going to go to the oxygen on the right, which is actually identical to the one on the left. So 6 minus the 4 lone pair electrons minus half of its bonding electrons, which is half of 4, that's going to give you 0. So oxygen has 6 valence electrons. It has 4 lone pair electrons. And we take half the bonding electrons, which is 4, and that gives us half of that is 2, so that takes us to 0. So if we take all three of those calculations, we see that the formal charge of 0 on all elements means that this configuration of carbon dioxide is the most stable. You can't get any more stable than 0, 0, 0, or however many atoms you have in that particular covalent compound. Now we're going to look at the molecule on the right. So we're going to start with the oxygen on the left there. So it has 6 valence electrons in its natural state. Now count the number of lone pair electrons. There's 2 on the top, 2 on the left, and 2 on the bottom. That's a total of 6 lone pair electrons. So that's minus 6. And then the bonding electrons. There's 2 of them between the oxygen and the carbon. So you're going to take half that number, so 1/2 of 2. And when you do the math on that, you get a number of -1. So oxygen has 6 valence electrons. Oxygen has 6 lone pair electrons, and we take half the bonding electrons, and that gives us a -1. So the -1 charge on the left oxygen means that it is less stable than a 0 formal charge element. All right, let's take the carbon in the middle. So carbon has 4 valence electrons in its natural state. You see that there are no lone pair electrons attached to that carbon. And it has 8 bonding electrons, so you take half of the 8, and you have 4 minus 0 minus 1/2 of 8 equals 0. So what it's saying is that this carbon in this molecular formation is just as stable as the carbon on the left. Okay, so the carbon's okay, it still has a 0 formal charge. Carbon has 4 valence electrons, carbon has no lone pair electrons, and we take half of the bonding electrons, and that gives us the 0. Now we look at the oxygen over on the right, which is not the same as the oxygen on the left. So it does have 6 valence electrons in its natural state. You notice that it only has 2 lone pair electrons, the 2 way over on the right, and it has 6 bonding electrons with the carbon, so you take half of 6. So 6 minus 2 minus half of 6, which equals 3, will give you a total of 1, positive 1. So oxygen has 6 valence electrons, oxygen has 2 lone pair electrons, and we take half the bonding electrons. Okay, so we put all of those equations together, and we see that they do add up to 0, -1 plus 0 plus 1. The formal charge, no matter what the molecule configuration, has to add up to the charge on the molecule. And carbon dioxide is an electrically neutral molecule. Okay, so that's going to be that if you don't get a charge of 0, that means you made a mistake in your arithmetic somewhere. Okay, but what we do see is that the oxygen on the left has a charge that's not 0, and the one on the right has a charge that is not 0, and that makes the molecule on the right less stable. So both oxygen atoms have a charge. This makes the molecule on the right less stable than the molecule on the left, where all the charges were 0. So this is the configuration of CO2 in nature. Now let's talk about something called resonance structures. A resonance structure is an alternate construction of a molecule. Ozone has a formula O3. Ozone contains 3 oxygen atoms. The central atom is connected to one of the terminal atoms with a single bond and the other with a double bond. If you were going to draw it, it would look like that. And you notice that the single and double bonds can switch places. So which of those diagrams is the correct one? Well, they're both correct. It doesn't matter which side you put the single bond on and which side you put the double bond on. And so those 2 configurations are called resonance structures. And one way to show resonance structure is to draw both configurations with a double arrow between them, and that's saying that they're both possible structures. Since the double bond could be connected to either the right oxygen atom or the left oxygen atom, it can be shown in both configurations with an arrow between them. A resonance structure is an alternate construction of a molecule. In nature, however, the second pair of electrons in the double bond is moving throughout the molecule, similar to the electrons in a metallic bond. They are said to be delocalized. Ozone can be thought of as having 2 1 and 1/2 bonds represented by the solid line and the dashed line. So this is another way of showing that it's a resonance structure. You would not write the 1 1/2. I wrote that just so you understand what it's really saying. It really has one full bond and then a half of another bond. All right, so this wraps up Unit 6 on ionic and covalent compounds, and we're moving on to a new unit in the next lesson.